Okay, so if you're just joining us on the video, we are doing sequences, and you're writing down these first 5 terms. And Red, you know the first term, right? What do you get when you plug 1 into this? You just get 1. So that's going to be 1 plus 1 over 3 minus 1. Not that I don't believe you, but I just want to show for anyone who isn't quite sure that it really is 1. There you go. Let's get the next one. Carson, what's the next number in this sequence? 3/5 sounds good to me. So 3/5. So you're just plugging in 2. And let's just get a couple more. Christian, do you know what the next one is? So you're just going to plug the number 3 into this. So yeah, 1/2 3 over 8, which is, or I'm sorry, 4 over 8, which is the same as 1/2. Very good. And then just a couple more, and then we'll be done with this. Hayden, do you have the next term? 5/11. Sounds pretty good to me, but if anyone has complaints, we can you can send them to Hayden. And then finally, Caleb, the final one. This is when we plug 5 into this thing. What do we get? Ooh, interesting. So I think that's 6/14. Is that right? So 3/7. I'm going to write it as 6/14 just in case anyone's like, hey, where'd that come from? So it's 5 plus 1 over 15 minus 1. Nice work. So that's the easy thing. Well, I don't want to say the easy thing, but it's sort of the easy way of going from the sequence to the numbers in the sequence. A harder thing, and this is sort of what I did in grad school a lot, was taking a sequence and trying to figure out what is the pattern in the sequence. And then, of course, it's not good enough just to, because I showed you yesterday the idea that different sequences have the same starting point. You have a block of numbers or a sequence of numbers. You never know, well, unless you can prove what the relationship is, you can't really say what the next thing is without, inductively. But still, we can assume, if you assume that these patterns continue the way that they are, see if you can come up with the formula for these sequences. So you're going to take look at what the pattern is, and then based on the pattern, can you come up with a formula? And I don't care if you start with n equals 0 or n equals 1. And actually, honestly, it's going to be easier if you start with n equals 0 for these two. And if you start with n equals 1 for these, for this one, I don't know about that one. You can start with whatever you want down there. So do your best. Let's see where we get, and then after this, we'll do a quiz, because this is sort of like the early homework, and the quiz is sort of like these. So that'll give you a little more practice. Oh, interesting. So there you go. You get a preview of the homework. Okay, so there's a couple of ways we can do this. So if you're not sure, it's okay. We'll talk through. That's the thing, is doing this is hard. And that's part of why there's this tool that's online for mathematicians who are interested in sequences, this online encyclopedia of integer sequences. But for us, these are actually pretty simple ones, but it is hard the first couple of times. So if you're not sure, it's okay. I'll walk you through it. But Braden, do you have any ideas about either a formula or just a pattern that you see with those numbers? Okay, very nice. 2 plus 5n. Now, if you're not as quick as Braden is in seeing that pattern, you might notice this about this, that you're adding 5 each time, aren't you? This is 2 plus 5 is 7. 7 plus 5 is 12. 12 plus 5 is 17. So each time you add 5. And so it makes sense that we're starting at 2. And then we just count the number of steps. Let's see, to get to the 17, we have 1, 2, 3 steps. So you're going to add 3 5s to 2 to get to the 17. So for Braden's sequence, he's starting with start at n equals 0. Just so you know, that's how he started. If you wanted to start at n equals 1, it's a little bit more complicated because you kind of have to go backwards and say, okay, we'll start at -3 plus 5n. I don't want to do that, but it is possible. Let's see if we can do the second one. And once again, if you're not sure, we can talk through. Eli, do you have any ideas for the number 2 down here? Ooh, nice. So we'll just so that we can distinguish, we'll call this one B. So B sub n is 3n plus 2. So very similar situation where you're adding the same number each time. So you're adding 3, 3, 3, and we're going to assume that the pattern continues, the obvious pattern. So I'm not going to try to trick you. The book doesn't try to trick you. Don't worry. These are just very straightforward. So 3 times some number plus 2, and of course here we're starting at n equals 0 as well. By the way, we have a name. We have a name for these 2 sequences. Both of these sequences are in a particular category. This isn't really that important for this class, but the next category is important. Well, it might be important, but I know for sure that number 3 fits a category that is very important for this class, but we'll name this one. This type of sequence, this is called an arithmetic sequence. And I know that when you look at that word, you think arithmetic. And you're probably thinking an arithmetic sequence. It's called arithmetic sequence, that when you use that word as to describe the word sequence, we're going to pronounce it arithmetic. But all that means is that you're adding the same number each time. So add the same number each time. So just leave it at that. So you can see here you're adding 3, 3, 3. Here you're adding 5, 5, 5. So whenever you see that, you're like, oh, that's an easy one. It's going to look something like this. You know, notice that the pattern, you can see it's sort of similar. The next one is not arithmetic because you're not adding the same thing each time, but I'll bet you can figure out what's going on. So take a minute and see if you can figure it out. And so you can either describe this with a formula, the way that we've been doing, or if you're not sure of the formula, just tell me what's going on. So Christian, what do you think? What's going on? Or do you have a formula for this third one?
I started at 1 and I had 1 over 2.
Oh, very nice. So C sub n, we'll call it C, is 1 over 2 to the n. Is that what you meant? Or what you said? I think it's what you said. So that looks good to me. Because if you do 2 to the first power, you get 2. 2 to the second power, you get 4. 2 to the third power is 8. 2 to the fourth power is 16. Very nice. Now that's one way to write this. Just a very slight change, which is, it's not, Christian did perfect. Good job. But if you wrote this way, 1/2 to the n power, then it's a little bit more obvious why I'm going to name it the way I am. So when you write it like this, it's hopefully obvious that what's happening is you're multiplying by the same thing each time. So up here we were adding 3, adding 5. Here, you're multiplying by 1/2, and then multiply by 1/2 again, then 1/2 again, and so on. So you have 1/2, 1/2 times 1/2, 1/4 times 1/2, and so on. Whenever that happens, we call this a geometric series, or sequence, sorry, geometric sequence. And of course, as you might guess, when we get to series, these will form a geometric series, but geometric sequence. And so here, I'll write this like this. There is a common ratio, because that's what's going to be important. The common ratio is the thing that you're multiplying each time. So think of it as, you know, if you make a ratio of successive terms, you take 2 successive, the next one divided by this one, you always get 1/2. That's what that means. But it really just essentially means you're multiplying by the same thing each time to get the next number. Okay, the last one's kind of hard because it's neither. It's neither arithmetic nor is it a geometric series or sequence. And you're not here, but you could have done it, I'm sure. So let's find someone who wants to try. So Darren, you want to talk me through this, or do you have any ideas as to what's happening here? Okay, so as you look at this, let's see if we can construct this. Let's ignore the bottom for a minute, and let's just deal with the top, Darren. If you had to describe the top, ignore the bottom, how could you describe that in a formula? Yeah, just n. Very good. So we'll start at 1, and it'll be just n. Now, Americo is going to help us out with the bottom. When you look at the bottom, ignore the top for a minute. What do those look like to you? Okay, so they're perfect squares, and you're like, okay, that's 4 squared, which is 1 more than 1 squared, and then 1 more than 2 squared. Very nice. So we've got that, and we're almost done. There's one last thing that I'm leaving out. We'll get to it. So there's n plus 1 squared on the bottom. The last thing to deal with is the, well, let's see if you recognize it. Karen, do you see what's missing from my formula that's over here somewhere? The negatives. We have to have negatives. And what do you notice about the negatives, Karen? Yeah, they alternate. You have a negative, then a positive, then a negative, then a positive. So this thing alternates, negative, positive, negative, positive. The trick to getting your sequence to have that is you just introduce this. You put a -1 here, -1 to the nth power. Now think about what that's going to do. When -1 is raised to the first power, you get -1. When -1 is raised to the second power, it becomes +1, and so the negative goes away. And then when -1 raised to the third power, you get -1 again, and so the negative is there. So it kind of turns the negative on and off, on and off. Very nice. So that's the formula for that one. Beautiful. All right, well, before we do the quiz, there's one more thing just for fun. So I dug out of my files this sequence. I think I told you about this student. So early on in my time at Temple University, I had a student come up to me after class and say, hey, can you figure out the number that's missing in this sequence? Let me show you the sequence that she showed me. So she showed me this sequence. She said, what number is missing? Oh, no, sorry. I have to say it right. Fill in the blank. Tell me what goes there. And I puzzled over it. I guessed. I was like, is it 63? Or no, wait, 66, right? 66? I don't know. There's no pattern. There's no pattern to this. And I guessed and guessed and guessed. And I was like, I don't know. And at the end of the summer, or this was like a summer class, like 6 weeks or whatever, at the end of the class, she disappeared. She never told me. And so 3 years later, I moved. I moved from northwest Philly, a little place called Andorra, inside the city limits though, so literally Philadelphia, down to the City Line Ave area, Drexel Hill, inside the city still. So I was still a Philadelphia resident. But here's the deal. I changed my commute. I used to drive down Henry Avenue to Broad Street and then down to Temple. But when I got to City Line Ave, I started taking public transit. And so I was sitting on the blue line one day, looking up at the wall, and I saw this. And I was like, oh my goodness, I just realized what goes in the blank. So I don't know if you see what I see, but this is the, what happened was I would either take the trolley or I would take a bus to the 69th Street station and then take the blue line in to here. And up here is where Temple University is. Not up there, it's like right here. But anyway, so I'm riding the blue line, the subway, and I look up at the wall, I see this, and so Millbourne. Millbourne was the answer. So I felt kind of I felt kind of ripped off, but I also felt like, I finally got it. And it's because I moved and started riding the subway. But anyway, so there's my story from that deal. So let's go ahead and try this. I've got a little quiz for you. I'll put it up on the screen as well. And then we're going to shift gears just slightly after the quiz to some other joyous sequence stuff. There's 2. You can send one over. Here's 2. Here's 2, 3, maybe. Is there 2 or 3? So you need one more. Very good. There you go. You can send one over to Red. 1, 2, here's 2. I'll send one over to, if I can get it to separate. There you go, Thomas. There's one for you. You want 2? Enjoy. Oh, that's just one. Sorry. There's one more in here. There's several. Here's another. Oh, why not? There's one more. Okay, I think I got enough. Everyone's got one. Good. There, and if you're watching from home, here it is. Okay. Okay, when you get done with this, just hang on to it for now. Hang on to it. We're going to talk about it in just a minute so that you can grade your own paper. So don't panic with that second one. If you're like, oh no, it's going to be okay. So you can, I'm pretty sure you're going to be fine with the first one though. So. All right, well, let's go ahead and take a look at what we have. Hang on to your own quiz there for a minute, or actually forever. So I'll just, because I didn't know how many of you had done the homework, so I didn't want to, thought this would be a good practice though. Also, you know how it works is the quizzes give you some hints as to what the test is going to look like. So let's take a look at this first one. Not hard, you're just plugging in numbers. Hopefully this didn't cause you a lot of grief. So here's my my answers, I've got a sub 1. I just listed them this way. If you listed them across, that's fine too. So you could have done this, -1, 1/4, etc. So I plugged in 1 and then 2 and then 3, and you start seeing a pattern, probably pretty obvious. Actually, I only plugged in the first two. So in my mind, I'm like, okay, -1/1, and then +1/4, and then I'm like, oh yeah, easy. You're just doing perfect squares in the denominator. So the rest of it is straightforward. So hopefully you got something similar, either written out like I did or like this. Either way is fine. 25th. So the issue with the second one that we didn't practice before, but that we're doing now though, is this business about beginning in with 1 instead of 0. Like if you began with 0, you're probably like, oh yeah, super easy. Beginning with 1, kind of a pain, but not that hard. Here's how I did it. You might have done something similar. I just said, okay, I'm used to doing this where n starts at 0. You want me to start at n equals 1? Fine. I'll just do this. So you got 4 plus, and then just subtract 1 from n times 3. Wait, duh. Sorry. That's not even right. This is not an arithmetic sequence. I got it wrong here, -10. Okay, I can't believe I was so focused on let's start again. Okay, you're multiplying by 3 each time. Okay, so 4 times 3 to the n is what I would want to do because you're multiplying by 3 each time, but that assumes that we start at n equals 0. And so then I'm like, well, okay, I'll just do this. If you really insist, subtract 1. There, now it's good. So if you do this, then the first term, n equals 1, you get 4 times 3 to the 0, which is just 4. The second term, 4 times 3 to the 2 minus 1 is 1. So that's 4 times 3, which is 12. This is 4 times 3 squared. That's 3 minus 1. 4 times 3 to the 4th, and so on. So sorry, I blew it there completely. This is geometric. So there it is. So there's what you should have. So there. Hopefully you probably did a better job than me. So yeah, if you began with n equals 0, by the way, you'd have something like this. N equals, or there's times 3 to the n. That's begin at n equals 0. So hopefully that makes sense. We're okay. Okay, so you can do this on your homework as well as on a test, but we do need to move on to the rest of the sequence stuff. So when we're dealing with sequences, one of the questions, we've got a couple different questions that we're going to be asking. One of them is, what happens in the long term? So what happens when n gets really big? You can picture the sequence. So to understand, sort of to get a feel for what's happening, you can either picture the sequence as terms like dots on a number line. So what I mean by that, I'll draw it here, but I have a picture that I'll show you in just a sec, is I've got a number line here, and when n equals 0, you have 0, that's a sub 0. A sub 1 is 1/2. A sub 2 is 2/3. A sub 3, 3/4. A sub 4 is 4/5. Do you see what's happening here? Then 5/6. The lines are getting closer together, but where do they end? That's the question, is what happens to this? And so you can kind of, I've got a better, well, this one was, the book made that one. But you can see what's happening here is that so here's a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, and then the numbers keep getting closer and closer to 1. And so you know what we're going to talk about is a limit. The limit as n approaches infinity of this sequence is going to be 1. Another way of picturing this is to draw a graph of this particular sequence. And what I mean by that is I'm going to draw this graph. F of n is equal to n over n plus 1. So I'm going to draw that graph. That's what I mean by plotting the graph of the sequence. So let's get rid of that ink for just a minute and show you what the graph looks like. And notice that on this graph, I've only plotted the dots that correspond with the integers because this is a sequence. Of course, you could connect this with a line and it would be a nice curve, but it's really the dots that I'm interested in. So graphing either the line or the dots is what I mean by graphing. Now notice that both of these indicate the same thing, and that is that as n gets bigger, the function values get closer to 1. So that's what we're trying to represent. And so when you see this happening, we're going to say that the limit as n approaches infinity of this thing is equal to 1. Okay, whoops, I don't want to go there yet. Okay, so we'll just pause there. So I just want to point something out, is that you've done this. You did this back in Calc 1. So this is old hat for you. Here, let me just do this right here real quick. If I was to give you this, the limit as n approaches infinity of n over n plus 1, which is essentially what we just did, you could do this. So just to remind you how you do this, you're going to use this fact. So I just want to show you this once, the hard way, and then I will be happy to wave my hands in the future, which is what you do, which I know it's fine. But here's the literal, like the technical what's happening here is this. You're using this fact. Here, this is a fact. You can call it a theorem if you want. 1 over n is equal to 0. So here's the little fact that we're using. We know that to be true. And so that is the fact that you use each time you do a limit. Now, I know what you're thinking. You're thinking, oh, I know how to do this. Take the coefficients, right? How many of you do the coefficients? Do you do the coefficients? The coefficient and numerator? No, maybe some of you? Okay, well, I'll show you. If you don't know what I mean by that, I'll show you. That's the shortcut. But the reality is that this is equal to this. Give me a minute. This is a little tedious. So that's why I only want to do it once. Multiply the top and bottom of this thing by 1 over n. And essentially what you learned back in Calc 1 was these would be x's, but you would multiply the top and bottom by 1 over the highest power of x, or n in this case. And so let's see, this will equal the limit as n approaches infinity of 1 over 1 plus 1 over n. And now we apply this little theorem down here to this, and you're like, oh, hey, we're all good. And so this equals 1 over 1 plus 0, which is 1. So the business with the coefficients, what that's referring to is this, that if you have the same degree polynomial on top and bottom of a rational function, then the limit as n approaches infinity will just be the leading coefficients, a fraction made up of those leading coefficients. It always works out that way. So here, just to do one more, and then we'll go back to PowerPoint. So if you have something like this, 3n squared minus 5n cubed over 2n cubed plus 7. So something like that. Go ahead and jot down what you think the limit of that sequence is. So, and then I'll show you when we get there. So using this, if you did it this way, which I'm not going to, but I'll speak it, to do it this way, the right way, I would multiply everything by 1 over n cubed, and then deal with that, and sort things out. But let's just do it the simple way. You notice that the degree of the numerator is 3, third degree, because of this. The degree of the denominator is 3, since they're the same. What you do is you take the leading coefficient. By leading coefficient, we mean the coefficient of the highest power term of the numerator and the coefficient of the highest power term of the denominator. You can work out the algebra if you want. Whoops, not a 3 down there, it's a 2. So the rule is, so let's just go over the full rule, is the limit as n approaches infinity of p of x over q of x, that if the degree of p is greater than the degree of q, this is a review of your Calc 1. At some point you had this. If this is the case, then the limit, then you diverge. Here, diverge. Just write it that way, diverge. So if the degree of P is less than the degree of Q, then the limit is equal to 0. And then if the degrees are the same, then you take the leading coefficients. The trick that I did up here in the highlighted. So there's the rule that you learned maybe back in calculus. So this is the shortcut. And then once again, the right way to do this is to apply this little fact to everything. So that's the correct way. This is the sort of cheater way. It's not really a cheater, it's a theorem. But bear in mind that it came from up above. Okay, so that doesn't really explain what to do in every case. So we're going to have to deal with some other stuff. So here's just a couple of illustrations before we get back to limits. Is that if you have a limit, there's different ways that you could approach a limit. You could have like your sequence go up above the limit and then kind of fall back down. You could have a sequence that kind of oscillates like this, but eventually gets to that limit. So there's different ways that you could end up at a limit. And so this is our general notation. We're going to call the limit L. So the limit as n approaches infinity of our sequence is going to be just L. That's too many words. So basically, we're just going to say that as n gets big, the numbers in the sequence get closer and closer to this limit L. It's just the same as your limit notation from Calc 1. One other thing I should mention that might be useful. Here, let's do this right now. Let's do this. What is the limit as n approaches infinity of, say, how about this? I'm mixing my stuff, x and n, it's n. N squared over 2 to the n. Ooh, that looks like fun, doesn't it? So what's the limit as n approaches infinity of this? This does not qualify for that thing that we did, the theorem that I showed you, but you have a tool. You have a tool that will help you do this particular limit. So here, I'll write it down in terms of x, because you might be more comfortable with that. Whoops, sorry. So let's do this with x instead of, so what's this limit? X to the second over 2 to the x. All right, so I don't want to put anyone on the spot with this, but there is a rule or a theorem that we used to do the limits like this. Does anyone remember the name? You remember the name? It is L'Hopital. You go to the hospital when you have something like that. L'Hopital. So a French guy came up with this, or maybe he proved it, I don't know. But the idea is you do the derivative, and this only works when you have a L'Hopital's rule indeterminate form. Indeterminate forms are when you have 0 over 0 or infinity over infinity. And in this case, it's infinity over infinity. So when you apply L'Hopital's rule, if you have a indeterminate form, you do the derivative of the numerator and the derivative of the denominator. This is what every beginning calculus student wishes the quotient rule was, which it isn't, but let's do these derivatives. So let's see who gets to do the numerator. Ethan, you're not here, sorry. But Michael G, you know the derivative of x squared, don't you? It is 2x, very nice, 2x. All right, Simon, oh, sorry, I got a little too excited there. You know what's coming, Simon. Oh, we want to know the derivative of 2 to the x. So what do you think? Do you know the derivative of 2 to the x? Do you have any guesses? 2 to the x, very good. 2 to the x. It's very much like the exponential function. The derivative of e to the x is e to the x. The derivative of 2 to the x is 2 to the x. Well, not exactly. There's a correction factor. Were you going to tell me the correction? Not quite? Yeah, there's a correction. Does anyone know what I need to multiply this by to get the derivative? You know it, Carson? It is the natural log of 2. Isn't that exciting? So we multiply this by the natural log of 2. So the derivative of any exponential function is just like e to the x, It's just that because it's not e to the x, you have to correct for the fact that you're not dealing with e to the x. Okay, so here, when I do the limit, plug in infinity, I get infinity over infinity again. So I have to do L'Hopital's rule a second time. I don't know if you're like me, but I actually got kind of excited when I was doing L'Hopital's rule and had to do it twice because I was like, hey, this is kind of cool. It's like this snowball effect. Okay, so let's do more derivatives. More derivatives. Landon, what's the derivative of 2x with respect to x? It's just 2. Very good. So let me write this down as a limit. All right, so that's going to be 2. So this is going to be L'Hopital. The spelling, you either have the S there or you don't. I don't know why. I've seen it both ways in different calc books. So we're going to do it again. Here we go. This is going to be, how about this? I believe it's always got that funny looking thing on top of the O though. Okay, Ben P, do you know the derivative of all of this mess down here? You would, very nice, because you're just, yeah, it's just a constant. So you're multiplying by another natural log. Hey, look at this. The limit as x approaches infinity of this is 2 over a very big number. 2 over a very big number is close to 0. In fact, that's what it is. So there it is. So don't be scared if you have something like this that you're like, I can't do that using my tricks. Well, you can use L'Hopital's rule. It'll be okay. So don't forget to use all of the tricks. So this, I guess, is also going to be 0 because those are linked. Okay, so next, where's my next thing? Here we go. Okay, so some boring stuff. Wait, is it time to go? Everyone's packing up? No. We got 20 minutes almost. Do I want to do this? Sure, why not? Yeah, let's do this for fun. So this is kind of a theorem, if you will, that if you ever have 1 over n to the r, the limit is always going to be 0. This is, yeah, that's not a geometric series though. So this is just something that's always going to be true. That'll be useful later on. And then there's this big, long list of rules that I would not suggest you copy down because as you're going to see, I just took them right here. I'll even tell you the page number. Here, I'll put it up on the screen and then I'll find the page so that you don't, there's this big, long list, but I just stole it directly from the book. Here it is. It's on page 697 if you really want to look at it. So this is page 697 in your textbook. And all this is this is just a list of rules to help us when we're dealing with sequences. All of these, by the way, are the same as the rules that you had when you were doing the sequence, or not sequences, limits, infinite limits for Calc 1. So the limits, it's the same rules. Just point out a few of these. If you're adding 2 sequences together, you can separate it and do one and then the other. If you're subtracting, you can do the same thing. The limit of a constant is just a constant. Like if you have a bunch of 1s, then the limit of that sequence is just 1. So here, the limit of a constant times a particular sequence is just that constant times the limit of that sequence. So these are just some things that will be useful. Everything is sort of the way you would expect it to be because you know about Calc 1. So all of the limit rules, but that's on page 697 if you need it. So we'll start easy and we'll move more difficult. Let me just make sure we can get through everything we need to. I think we can. So we'll start easy. This one we've already done, so I'm not going to make you suffer through this again. You already know. This one is convergent. It converges, and the limit as n approaches infinity of n over n plus 1 is equal to 1. So we did that one already. So that one we're good with. But this is the language we're going to use. Converge just means that we have a number at the end of the rainbow, so to speak. And if you diverge, it means that there is no number. It just grows or maybe toggles or whatever. We'll have a few examples of divergent sequences in a minute. So let's go ahead and do this one. Does this converge or does it diverge If it converges, then tell me the number that it converges to. All right, Michael H., what do you think? Does this thing converge or does it diverge? It converges. Very good. And do you know the number it converges to? Pi? Oh, no, I know. I figured you said that. It sounded like pi to me. But yeah, 5. You're right. 5. Very nice. Okay, very good. Very nice. This thing converges. So converge. Okay, I'm worried that I don't have any. Yeah, I may have to invent a couple of examples that are not on my list here. Let's try this one. What about this? So a sub n is equal to n over 1 plus the square root of n. Does that converge or does it diverge? Take a minute, see if you can work it out. And if it does converge, you can tell me the limit. Okay, find a volunteer. All right, feel free to discuss with your neighbor as well. It's always a good way to do it if you're not sure. All right, let's see how you did with this one. Eli, what do you think of this? Does this thing converge or diverge? Really? What's the limit? How do you do the limit? I don't even know how to do this limit. Okay, so we're going to use that little trick. So technically, I just want to point out that even though this trick works, even when you're dealing with things that aren't polynomials, which this is not a polynomial, so you think, oh, well, I guess we really can't use that trick, but it does work with things like this. So anything that looks like this, the degree, and I'm going to use that in quotes because that's not a polynomial, but you might say, hey, look, this is into the 1/2 power. This here is into the first power. So degree of the numerator, the highest power in the numerator, maybe that's the way we could say it. The highest power in the numerator is 1. Highest power in the denominator is 1/2. So 1 is bigger than 1/2. This will diverge. So this one diverges. By the way, you might wonder, well, if we didn't apply that trick, how would we do this? Well, we do it the way that we suggested with the 1 over n thing. So what was that? Oh, you could also do L'Hopital. You're right. L'Hopital. Just trying to think. Yeah, L'Hopital actually would be quicker. Yeah, let's do L'Hopital. Thank you. Save me from trying to do a bunch of algebra. So yeah, L'Hopital. The derivative of n is 1. The derivative of 1 plus radical n is 1/2 into the negative 1/2. And that equals 2 square root of n. Oh, limit. All right, yeah, L'Hopital is way easier, and that definitely diverges because you don't even have a fraction there anymore. So very nice, good job. Okay, so that thing diverges, and so that would be the answer. If it diverges, you just say it diverges. All right, next one. Let's try this one. Harder yet. I know I keep throwing bizarre things at you. Let's see if you can do this. I've got like 3 different ways we can do this. So if you're not sure, I'll give you options. Here, I've got it right on my head here. So there we go. So I'll show you 3. I won't complete them all because it's just a lot of work. All right, let's see. Find a volunteer. Andrew, what do you think? Did this converge or diverge? It diverges. Excellent. How do you know? Okay, you're going to use the degree rule. That was going to be my first option, is you use the degree rule, but here you have to sort of massage it a little bit. So the degree rule, Let's talk about the degree in the numerator. Numerator is easy. That's got a degree of 2. The denominator, that one's a little bit harder because what does it mean to, degree of that thing? Well, you can see that the highest power is n cubed, and then you're going to do the square root of n cubed. So you could do that, which is a little bit cheating, but I'll accept it. So that would give you a degree of 3/2, and the degree of the numerator is higher than the quote degree. It's not really a degree of the denominator. So that's option 1. Option number 2 is to do this. You do L'Hopital. I guess I should capitalize, which is, this is going to be painful. So I'm not going to do it, but you could. You could do L'Hopital. So another way is to do this. Now you might say, well, what good is that? Well, if a sequence converges, then when you square that sequence, it will also converge. So let's just square this and get rid of that square root. So a sub n squared is n to the 4th over n cubed plus 5n. That clearly diverges. And so, of course, the original sequence will diverge as well. So technically what I'm doing, by the way, is I'm using, just a minute, that third way is, I'm not cheating, don't worry. I'm using this down here, that the limit as n approaches infinity of a sequence to some power, you can do the limit of the sequence raised to the power. And you might say, well, what is the power that you're using? Well, here, I'll show it to you once I find this again. Is this it? No, that's something scary. So here it is. So here's what I do is I'll call this b sub n. And then this thing diverges. And so what I do is I do the limit as n approaches infinity of the square root of b sub n, which is b sub n to the 1/2 power. So this will be the square root of the limit as b approaches infinity of b sub n, which is essentially what I'm looking for up here. So that diverges. Okay, so however you cut it, though, this thing diverges. So what is this? This just says that you can ignore the positives and negatives if you're dealing with a limit equal to 0. So if something goes up and down, you can get rid of the positives and negatives. And then if you have a function that converges to a function of a sequence that converges to a particular limit, then you can just apply the limit inside that function, which is convenient. This only works if you have a continuous function, but most of our functions are going to be continuous. So with that said, let's take a look at this. What is the limit as n approaches infinity of sine of pi over n? So let's go ahead and try this out. So instead of worrying about the sign, so this actually illustrates both of the things that I was showing you there. If you were to graph this sine of pi over n, you'd start off with the sine of pi, and then the sine of pi over 2, sine of pi over 3, sine of pi over 4. This thing, it doesn't fluctuate that much, I guess. It's always positive, except for the first one. No, the first one's 0. But anyway, you could imagine with sines and cosines, you might fluctuate up and down. In this case, this one doesn't, I suppose. But what is this limit? So to do this limit, since this function is continuous everywhere, I can move that limit inside the function and just do this. And do the limit. So let's find someone to do that limit for me. Just ignore the sign for a minute and just do the limit. You're not here. You would know it, though. Okay. I feel like I've hit on everyone almost. Who hasn't gotten picked? I don't remember. Oh, Maggie hasn't. Maggie, what's the limit as n approaches infinity of pi over n? So it's just a constant over n. So it'd be like, no, we're doing a limit as n approaches. So imagine putting a really big number into this. What's pi over 1,000,000? Or pi over 1 billion? or maybe pi over a trillion. What are these getting closer to? Yeah, it goes to 0. Yeah, so very good. So the limit of pi over n, I know the pi is confusing. You see a pi there, and it's like, what's going on? Thought Pi Day was Friday. It was, but yeah. So this sine of 0, very nice. And the sine of 0, we all know what the sine of 0 is. It's 0. So the limit of this thing is also going to be 0. So don't be scared to apply your limit inside a function. Let's see, anything else that we have to do here? I don't know. I guess there's some language that we're going to use. We might as well. We have a few more minutes. Let's deal with some definitions, some language. Let's see. This one is good. So r to the n. So this this sequence. This is a geometric. So geometric sequence will converge if this common ratio is between -1 and +1, and it diverges otherwise. And so the actual number that you converge to will either be 0 or 1, depending on what the common ratio is. The only time you converge to 1 is if your common ratio is 1. So just as an example, if you have this sequence, 1/3 to the nth power, that will converge to 0. If, on the other hand, I have this -5/4 to the nth power, since 5/4 is bigger than 1, that will diverge. So this is what we'll be doing over the next couple of weeks is we will be taking sequences and series when we get to it, but sequences, and we will classify them and then deal with properties so that we can use those properties to help us out as we go forward. Okay, another thing, another definition is the idea of increasing or decreasing sequences. So a particular sequence increases if the sequence values get bigger. Kind of makes sense, right? Well, there you go. So increasing means they're getting bigger. Decreasing means they're getting smaller. We've had examples of both of these. Let's see if we can go back here to the very beginning and show you this picture again. Where did the picture go? There it is. So there it is. So that is an increasing sequence. It's increasing. And then we don't, do I have a picture of a decreasing? I do not. Neither of these are increasing or decreasing, so they do both. So increasing, decreasing, and then monotonic means that it is going one direction. Monotonic, one direction, either increasing or decreasing. That's all we care about with monotonic. So I don't have good pictures of decreasing, but I have another picture of an increasing sequence here. Let's see, is there anything else? Let's do this one. That's bounded. Yeah, so bounded sequences. Not every bounded sequences are convergent. What I mean by bounded is that your sequence numbers, your sequences are always between certain, like for example, a sub n is always between -1 and 1. So it's bounded, but this particular sequence does not converge. The reason it doesn't converge is because if I wrote down the values of this sequence, notice that they toggle between positive and -1, and so these don't settle down to any number. And then this is a monotonic sequence, 1, 2, 3, 4, 5, but it does not converge. However, if you have a monotonic and bounded sequence, that will converge. So if you know that it is always increasing, and if you know that it's bounded, then you're for sure going to converge. Or if you're always decreasing and you're bounded, you'll always converge. All right, so you can do hopefully the whole of 11.1 if you haven't done it already for tomorrow, and we'll have a quiz similar to what I gave you today that we didn't collect, but I'll actually collect the one tomorrow. So stick around if you want to chat. I'm going to stop the recording, and then you'll have a happy Tuesday.